Hello, everyone. Good morning, good evening, good afternoon, wherever you are joining us from in the world. We really appreciate you taking your time to spend it with us here today. My name is Jamie Singleton, Senior Program Manager on the .NET Community Team at Microsoft, and I am joined here with my good friend and colleague, Cam Soper.
Hello, everybody.
So today we have a lot of really exciting stuff to show you. I cannot wait. We have been planning for this all month. We are going to be talking about IoT, or the Internet of Things, for .NET libraries. And we have a lot of stuff to cover, so I'm going to let Cam jump right into it. Yeah, let's see where we go.
Well, thank you, Jamie. Yeah, as everybody mentioned, today is IoT Day on Let's Learn Live. And what do we mean when we talk about IoT? We're talking about Internet of Things, which is really kind of a broad catch-all term for running code on little computers that can be put kind of everywhere. And the really cool thing about this is we can put like sensors in different places, or we can put relays in different places. So what this means is we can, through code, monitor and control the world around us. So this is really big in like industrial situations or home automation situations, various scenarios like that. So to give just a little bit of a primer on the different kinds of IoT devices, I'm going to start off with just a little bit of show and tell. So if we could throw my desk up on the monitor.
Yeah, there we go.
This is, here, let me change the orientation. This is a Raspberry Pi 4. And this Raspberry Pi, this is like the latest generation of Raspberry Pi devices. And everybody knows what a Raspberry Pi device, I won't say no, they've heard Raspberry Pi. Raspberry Pi is a general purpose computer, right? It's basically just a very small PC with a low powered processor and a limited amount of memory. But they can run lots of general purposes, lots of general purpose code on there with all kinds of things that they can connect to. We're going to come back to this row of pins later on. If you have a Raspberry Pi 4, great, you can do what we're going to show you today. If you have an older Raspberry Pi, like a Raspberry Pi 3, this is also great. And you'll notice the main difference between the 3 and the 4 is the 3 has a full-size HDMI port, and the 4 has 2 mini HDMI ports. Beyond that, they're basically the same form factor, and all the code we're going to show you today will run on either one. We can also run on Raspberry Pi 2. Now, Raspberry Pi is just one kind of it's just one kind of single board computer for IoT scenarios. There's lots of others. There's BeagleBoard, there's Hummingbird, Orange Pi is out there. What else have I seen? That's probably enough examples of that. The other type of IoT that we're not really going to go into today, but is something that I would encourage everyone to explore later on, is when we talk about microprocessor devices. Microprocessor devices like this one. This is an Azure Mqtt. I forget the number that goes with it, but Mqtt IoT kit something. This is a super low power processor and very limited amount of memory device that is really, I think, better for a lot of scenarios where you're putting sensors in weird places and you don't want to have to provide a large amount of power to them if you want to operate off of like batteries or whatever. To develop for this device, you would follow the same kind of development processes that you would follow for like Arduino devices. And then we have a video later on to talk about this device. This is another microprocessor device. This is a Wilderness Labs Meadow. Now, the cool thing about Wilderness Labs Meadow is, whereas we are going to, for the Raspberry Pi, compile our .NET code and run as a .NET executable within the Linux operating system on Raspberry Pi, Meadow works a little bit differently. Meadow natively understands .NET. So you compile your .NET code into some sort of byte language, and I don't know like the Meadow level details, but long story short, it gets deployed to this little thing, and it's super low power, super inexpensive, and we'll have more about that later on. So to get started, I'm going to go to my browser here. And I'm going to go to aka.ms/learn.net IoT. This is going.
Yeah, for those of us following along, feel free to head on over to that site as well, and we can start doing the workshop together.
Now, this is a Microsoft Learn module. If you're not familiar with Microsoft Learn, it's an interactive learning environment that keeps track of where you are in the content. You can come back and continue it, different bite-sized chunks of it at different times. Some of the content that we have out there also enables a sandbox where you get to play around with Azure services free of charge. We're going to hopefully get to that later on in the presentation. So this Learn module, let's look at the prerequisites real quick. We're expecting you to have an intermediate knowledge of .NET. The reason for that is we do a lot of, we're working with Visual Studio Code. We're working with .NET SDK directly, command line operations. If this is your first exposure to .NET and C#, you're probably not going to have a good time. And I would strongly encourage you to go check out some of the beginner C# content that we have before doing this module. Also, just having a basic understanding of Raspberry Pi and being able to install the OS and being comfortable configuring the OS, that's also a prerequisite. That is covered in great detail by the Raspberry Pi docs. And then finally, we're going to be using .NET SDK 5 or later. Now, as far as hardware components, you need a Raspberry Pi device, 2 or greater. I've showed you a 3 and a 4. I need you to have it pre-configured with Raspberry Pi OS. So if you're watching live right now and you haven't done that, I'm going to recommend you just kind of follow along and come back and watch the recording later on. You're going to need a BME 280 humidity, barometric pressure, and temperature sensor breakout. I'm going to go back to my desk and I'm going to show you what one of these looks like. That's the breakout we're talking about. This one is from Adafruit. I also have some other ones here that are just some generic sensors. Same here. Let me get it to focus. Focus, please, camera. Yeah, that's good enough. Anyway, it's these are generic BME 280 sensors that I got off of Amazon. They work basically the same. You'll see in the module where there's some notes that say if you're using something other than Adafruit, it might use a different address, and we'll get to that when we get to it. So we'll need these sensors. We'll need an LED, so just a light emitting diode, a 5 millimeter light emitting diode like this. We're going to need a resistor. Now I'm going to use a 1K ohm resistor for this module. You can use a 220, you can use a 330. I just said 1.0 K ohm because it's a nice round number, and that's what I've been using for testing. You're going to need some jumper wires. So jumper wires are wires that have little pins on the end that you can plug into a breadboard, like what we have here. This is the breadboard. We'll talk more about the breadboard here in a minute. And then you technically don't need it, but I strongly recommend it. This is what we call a Raspberry Pi Gpio Breakout board. And we'll go more into what it does here in just a moment. So with that, let's step out of the introduction and, I don't have my navigation buttons, out of the title screen and go into the introduction. Here we go. So the introduction talks about how .NET runs on all these different platforms and IoT devices like we have earlier. We go over the prerequisites again. And this part is really important. I want you to have Raspberry Pi OS installed on your device. You can use the light image if you want, because we're not going to use the desktop. And then after you have Raspberry Pi OS, I need you to follow the instructions of the Raspberry Pi documentation and make sure you've enabled SSH and I2C. Okay, we're going to use SSH to connect remotely. And I'm sorry, I said I2C. It's actually referred to as I squared C. I keep mispronouncing it. I squared C is a type of serial bus that we are going to use to communicate with our humidity sensor. And then the last thing before we dive into actually working with some of this hardware is to talk a little bit about the scenario that we're the hypothetical scenario that we're embracing as part of this module. Suppose you work for a company that makes cheese. And of course, cheese aging is a process that requires specific temperature and humidity parameters, right? And this company that you're working for, they use a cave to age their cheese. They've built some racks somewhere in a cave somewhere, and they age their cheese in this cave, and they have some standards that they've set. Right? They want to keep it around 50 degrees Fahrenheit with a little bit of variance and a humidity level between 75 and 95%. And they have tasked you with building a sensor to monitor this and to also activate a fan to control the humidity. So that's what we're doing today. We're building a device with a Raspberry Pi to monitor the temperature and humidity and to activate a fan as we need to. Now, we don't actually have a fan here. Instead of a fan, I'm using the LED to stand in and represent a fan. If we actually had a fan, it would made that a prerequisite. I just know that I would probably regret it. So the prerequisite we went with was an LED, and the LED is just kind of filling in for us. So I'm going to walk through the content on this next unit again. It talks about the Gpio header and the modules and everything. Let's go back to my desk. So let's grab this Raspberry Pi 3 here. This array of pins is called the Gpio header. Gpio stands for General Purpose Input and Output. And this Gpio header supports a number of different protocols for communication. It also supports being able to just turn a pin on and off to output a low amount of voltage. That Gpio header has, I think, these 20 pins, and they all have different purposes. They're all documented. There's images that you can get at the Raspberry Pi documentation site or on the .NET IoT documentation site that lists all these out. But personally, I don't like interacting with the pins directly on the Raspberry Pi. It's just such a pain to count them all and know which one's which. So I prefer to use my Gpio Breakout. Now, the idea behind a Gpio Breakout is it has a little 20-pin ribbon cable, and you connect the ribbon cable to your device on one end, and then on the other end, the breakout, you can plug right into a breadboard. So what does this do for us? Well, the breadboard is a device that's made for prototyping electronic components. All of these pins in these side strips down the length of the board are connected. There's two strips here, negative and positive. The idea is that you provide power for all your components on these strips. And there's another one on the other side, another set of them rather, on the other side, negative and positive. And then in the center, all of these strips of pins are connected laterally. So for example, looking at my Gpio Breakout, I'll wait for the camera to focus. Looking at my Gpio Breakout, if I wanted to, say, interact with the this ground pin on the Raspberry Pi, I could plug my jumper wires into the holes right next to the ground pin on the Breakout, and it would be exactly the same as plugging it in directly to the Raspberry Pi. We've already discussed the breakouts we're going to use. I'm going to use this Adafruit BMI 280 breakout to start. If we have time, I'll switch out with my generic BME 280, but it's literally one line of code that I would change just to change the address, and it's other than that exactly the same. And then the last thing that I want to show you is a relay module. Now, we're not using a relay module today, but we're hypothetically simulating a relay module with an LED. Now, this relay module is a double relay module. It actually provides 2 relays. And the idea is that you provide power to it with the voltage and ground pins here, and the 2 input pins just listen for a low amount of DC voltage. And when they get a low amount of DC voltage, they trigger the corresponding relay, which will activate a device. So this is the type of thing that you would use if you were going to control a fan. Like in a cave, a fan is going to be probably, in the US anyway, is going to run on 110 AC. Voltage, which is going to be, it's more than what you're going to be dealing with these GPIO pins. So the idea is that you can control the larger amount of voltage with a smaller amount of voltage. Now, again, for purposes of for our discussion today, we're not actually going to trigger the relay. We're going to just trigger. We're going to trigger this LED. It's exactly the same code. Well, I say exactly. There's one little thing that might be different, and we'll get to it when we get to that. And that covers all the components. So let's put it together. We're going to build our device using this breadboard with the diagram that we have on screen. And I'm actually going to do this live. And I'm going to do it upside down so the orientation on my desk matches the orientation on the chart. So I've already got my breakout positioned. I'm going to come along here, and we're going to put the BMI 280 right next to it. And then I'm going to put a little bit later on, I'm going to put I got to look at my diagram here. My LED is going to be the anode, the longer positive lead is what goes to pin 21. So we'll put that here like that. And then between the negative lead and ground, we'll put a resistor. Now, you wouldn't actually need to use a resistor with a relay. The resistor we're just adding so that our 3.3 volts of DC current coming from the Raspberry Pi doesn't burn out the LED, because that's really too high for an LED. So the resistor is just is there to reduce the voltage going to the LED and not burn it out. In a real world scenario with a relay, you would just wire it to the relay. And now I'm going to connect all this stuff with jumper wires. I've even color coded my jumper wires to match the diagram. I'm going to bring my diagram back up here. So just briefly, we'll try to do this quick. This is actually the fun part. I don't know if you ever played with like those snap circuit kits when you were a kid. I did. I never knew what I was making. I always had to follow the book. It wasn't until I actually got into this IoT stuff that I actually learned any idea of what I was actually doing. So let's wire up the 3.3 volts to the voltage in on the BME. There we go. We're going to do got to look at my chart again. Oh yeah, I got to wire up ground. Ground. Which ground did I use? I used the middle ground on the chart. Ground. Let's do ground from the BME to ground. Looks right. And then we need to wire up the actual data connection from the BME. On the BME, where we need to find a pin labeled SDI. If you're using a generic one, it'll be labeled SDA. But anyway, we're going to find that SDI pin, which is this one here. I'm using the wrong wire, which is this one here. And we're going to connect it to the SDA pin on the breakout. There we go. And we need the SCK pin on the BME. and that needs to go to the SCL pin on the breakout. And then I believe I've got everything wired. So just to review, that's 3.3 volt on the breakout to, oh, here, let me add some light. 3.3 volt on the breakout to voltage in on the BME. Ground, I put that to the ground strip here so that I can connect ground to the ground strip. And then also this resistor I've got connected to ground. We have SDA on the breakout connected to, that's the blue one, so that's SDI on the BME. We have SCL, and it's connected to SCK on the BME. And then lastly, we have pin 21 connected to the positive lead, the anode on the LED, which then goes, the cathode, the negative lead, goes to the resistor. So that's our device. That's all the wiring we have to do for our device. If I was going to use my generic BME instead, there we go. If I was going to use my generic BME instead, you notice that the pins are labeled a little bit differently, and those are accounted for in the notes. All right, so that's it. That's the hardware. We should have a device. It's not tested yet, and I just built it live, so it's probably not going to work. Maybe it will, but we'll find out. So now that we've built this hardware, I'm just going to go ahead. I'm going to connect it. I've got a Raspberry Pi 3 here in a nifty little Azure case that I 3D printed. And see that little Azure logo? Isn't that fun? I'm going to go ahead and connect it. Now, my device is powered up, and I've done this many times. You might want to do this when your device is not powered. It's probably safer. You probably shouldn't do it when it's powered up like I just did, but I just did. Okay. Oh, and you can see we do have power. My BME has a little green light now. So it's at least getting voltage from the Raspberry Pi. So we at least know that part's working. All right, so now it's time to do our software.
Hey, Cam, do you have a couple time for a couple quick questions before we move on? Just since that was like the initial hardware installation.
Absolutely, let's do it.
Okay, great. I'll make them quick. So we have a couple great questions out there. Ray from Learn TV says, does the Azure Sphere count as an IoT device? I kind of think of it as a carrier board of sensors.
You know, that's a good question. Unfortunately, I'm not real well versed on Azure Sphere. That's kind of its own little thing that I haven't seen a whole lot of crossover with that in the .NET area yet. Maybe I know we have an expert moderator, Laurent, who is helping answer questions in the chat. Maybe he's seen something there, but I really haven't had much exposure to Azure Sphere. Sorry.
No worries. I just wanted to ask that really quick. Yes, we do have a moderator in the chat, so feel free to ask your questions there. We will get to as many as possible. Yeah, and I guess, yeah, is Windows IoT going to get an update for Raspberry Pi 4?
That's an interesting question. I don't have any idea. So people, just to give a little bit of background, the question there is Windows IoT going to get a update for Raspberry Pi 4? I honestly didn't even know that it didn't have the capability for Raspberry Pi 4 because I never use Windows IoT. Windows IoT is a version of the Windows operating system that is, it's a very scaled back, kind of minimal version of Windows designed specifically to run on single board devices like Raspberry Pi. I've done very little with it. Raspberry Pi, I think the most compelling scenario with Raspberry Pi is Raspberry Pi OS, the Linux OS, because it just opens up your world to all kinds of different things inside and outside of the .NET ecosystem. So that would be my recommendation, honestly, is if you're doing Raspberry Pi, do Raspberry Pi OS. I'm not much of a Windows IoT expert.
Okay. Alrighty, we'll keep those questions coming. We will get to them. We will also save some more time for more direct Q&A, and I'll let you keep going with the workshop.
Sure thing. So this is the part where I need to introduce everyone to the .NET IoT libraries. So the .NET IoT libraries is a collection of two open source NuGet packages, system.device.gpio and iot.device.bindings. System.device.gpio really provides kind of the low-level hardware interface. It's good for flipping bits on and off, and it implements several protocols like the I2C, the SPI, so that's serial peripheral interface, pulse width modulation, and others. Now, when you're working with individual devices like the BME 280, you may not want to actually deal with the low-level I2C communication. You may just want to interact with your device as some kind of an abstraction to say, hey, give me a temperature reading, give me a humidity reading. And that's where iot.device.bindings comes in. iot.device.bindings is a community-supported open source package that contains dozens of bindings for all kinds of different commonly available IoT devices. For example, the BME 280 chips. If you check out the .NET IoT documentation, there's a quick start on there that takes advantage of a binding for this device. This device is called a Raspberry Pi Sense Hat. It's really kind of a cool thing. It's got like 6, 7 sensors on there. I forget the count. And mine looks a little bit different because I've got some black film over the LEDs because they were way too bright to photograph. So I got some semi-transparent film to put on there to reduce the lumens generated by the LEDs. But the idea behind the Sense Hat, oh dear, I don't have my little adapter on the bottom. The idea behind the Sense Hat is that it just, like a hat, just sets on top of the Raspberry Pi and provides all these, like I said, 6 or 7 different sensors. There's like an accelerometer and a gyroscope and a humidity sensor, temperature, I think 2 temperature sensors, if that's right. And of course, this whole little LED matrix, little joystick here. The .NET Quick Start for IoT on the IoT Libraries documentation site, which we will share as a resource later on, includes a quick start for this Sense Hat, where literally all you have to do is run one line of script on the Raspberry Pi, and it will download a code sample, compile it, and run it, and make this thing working for you in under 5 minutes. So, and it takes advantage, the reason I brought that up is it takes advantage of one of those IoT .device.bindings classes. So kind of spinning off of that question that we had earlier about Windows IoT Core, where can we run this stuff? Where can we run .NET with the .NET IoT libraries? Well, the answer is anywhere .NET is supported. So that includes Windows 10 IoT Core, it includes Raspberry Pi OS, it includes Ubuntu, it includes Mac OS, it includes a whole lot of places. So the hardware platforms specifically targeted by these IoT libraries are these single board platforms. Not so much on the microcontroller platforms, although there is some in there. The real target for these is these single board computers. Just a note, I'm going to call out this note here too. We mentioned earlier Raspberry Pi 2 being supported. Anything prior to Raspberry Pi 2 is not going to be supported. So Raspberry Pi, like the initial Raspberry Pi 1 devices, those aren't supported, and Raspberry Pi 0 isn't supported. Reason being that these work on an ARM v6 processor, and ARM v6 is not supported by the .NET IoT libraries. Actually not supported by .NET at all. So before we move to the next unit, we're going to check our knowledge. The .NET IoT libraries support which operating systems? Well, we just covered that. They are supported on any of them. Yes, any of them. And Jamie, maybe you can help me out here. Which of these is not a true statement? System.device.gpio enables communication using several IoT protocols. IoT.device.bindings wraps that package to streamline communication with IoT devices. All versions of Raspberry Pi support .NET, or the .NET IoT libraries are composed of 2 open source NuGet packages.
Oh, okay. So I'm thinking, B or C. Does it really support
The
all
correct
versions?
answer is C. So
It
not
really
all
does
versions of
support all of
Raspberry
them.
Pi. Yep, the Raspberry Pi devices that use the ARM v6 processor are not supported. So this one is not a true statement.
Congratulations! We passed our first portion of the workshop.
I mean, I should hope. I wrote it. All right.
Excellent.
So finally, we get to the code. I'm gonna pop my little Learn module over to one side. I'm gonna open Visual Studio Code on the other. I'm gonna open up a little terminal here. Everybody has, in Visual Studio Code, everybody has their favorite way to make new projects. I just do it in the terminal. And I know I'm going to get questions on this. I'm just going to respond to it before they get asked. Why does my terminal prompt look so weird? It's because I use a PowerShell add-in called Oh My Posh. ohmyposh.dev. Right? And it's a nifty little add-in for PowerShell and other shells that will give you like a customizable prompt. So I use that just to head off any questions. All right, going back over to Visual Studio Code. I'm going to make my new project. I keep all of my code on my D drive in a directory called source, and I am going to, just following along with the instructions here, going to make a new console app. I'm sorry, I got ahead of myself. I was not here. I'll just copy and paste the code. There we go. I forgot my -O command switch. That -O command switch, what that does is it says create a new directory for this project named this, and I forgot it. So whoops. All right, so cheesecave.net. I'm in that directory in the terminal, but Visual Studio Code doesn't see. I haven't opened any folder yet. I have a shortcut in the terminal to reopen Visual Studio Code pointed at the current folder. We're going to type code dot, that's current folder, -R to reuse the current window. So I've got the project loaded. If we look at the project file, we haven't got any references in. So let's go ahead and add our references. Go back again to my terminal, and I'm going to, again, just paste in these .NET add package lines. So I'm adding the latest versions of system.device.gpio and iot.device.bindings. So there we go. We've got our project references. And then I'm going to go into program.cs. Don't have a lot of room here. I'm going to go into program.cs. I'm going to get rid of all that. I'm going to replace it with the code from the module. Let's look at this code a little bit. So what are we doing? So we have all of our using statements here at the top that bring in all of our namespaces. We set a variable called pin, and we set that to 21. And we also set a couple of Booleans just to track program flow. And then I initialize the GPIO controller. So the GPIO controller, this is an abstraction that represents just the pins and the other functions of that GPIO pin header on the Raspberry Pi. And then my code is going to open that pin 21 and write pin value.low. So what does pin value.low mean? Well, with these GPIO pins, there's actually several different states they can have. They can have no current. they can have the lowest amount of current available, or they can have the highest amount of current available. And we're saying, okay, we're going to turn on that pin, and we're going to set it to the lowest amount of voltage available. Logically, this is off. This is a little bit different than what we're actually going to do with relays, though. In a relay, like the little relay modules I use, pin value.high is off and pin value.low is on. So that's the only difference between what we're doing with the LED and what we're doing with the relay. Is with a relay, you're going to set pin value to high. And with the LED, we're going to set it to low to start for off, right? The next thing our program does is it creates a variable to hold some I2C connection settings. And we pass in the ID of the I2C bus on the Raspberry Pi. That ID is 1. And we also pass in the address of the device that we're going to be using. For BME 280s, there's a enum in the somewhere in the namespace that defines. I'm not getting my IntelliSense. Oh well, it defines two addresses: default I2C address and secondary I2C address. This is important if you're using one of the generic BME 280s, because some of them use the secondary I2C address. So you would want to come in here and change that. But if you're using one of the Adafruit ones, the default is going to be fine. Then we create a reference. I'm using what's called a using declaration here to scope this reference until it automatically finalizes it when it falls out of scope. To create an abstraction called I2C device created from those settings. So we're creating a device pointed to this address on this bus. And then the final thing we do is we initialize a BME 280 object, passing in that I2C device. It's just another layer of abstraction. But now we have our abstraction, our BME 280 abstraction. So on the console, we can just write out the current status. Let's look at what that write status does. So it says, all right, my device is my fan on or off? Well, it basically just displays the content of that Boolean. It uses a ternary expression to display on if the fan on Boolean value is true and off if it's false. Then it displays the temperature and the humidity that it got from the BME 280. So we start this method by reading the BME 280 and getting the read result as an output object. And that output object exposes temperature, humidity, and barometric pressure. And the really cool thing that the developers of this class have done is they use an open source package, units.net. I'm not sure what it's called. It's the units. Anyway, they use this open source package to provide all these automatic conversions, right? So you have temperature.value, but value has, and again, I apologize, my IntelliSense isn't working right now, but it has degrees Celsius, degrees Fahrenheit, I think it has degrees Kelvin. So you just say, okay, give me the readout. I don't have to do any conversion. So write status gets that and writes all that out to the command line. And then the our control loop just sits there and waits for text commands. And our text commands are, if I type fan, it toggles that fan variable, right? And when we toggle the fan variable, sorry, there's the toggling. But when we do it, we had that pin 21 that we were interacting with earlier. We set the value to the opposite of whatever it is. If it's low, we set it high. If it's high, we set it low because we're turning the fan on and off. Again, this is actually reversed from what you're actually going to see with an actual relay, but the LED is just standing in for a relay in this case. We have a status command to just write the status again, and we have an exit command that sets exit to true, which is, again, it's just a control loop variable to get us out of the loop here. And then the last thing we do before we end the program is we close the pin. So there's our code, and we've gone over the code. That's great. Does it build? Let's see if it builds. .NET build. Looks like it builds. All right, so how do we get that over to the Raspberry Pi? Well, I'm glad you asked, because that's the next step. So there are two types of deployment in .NET. And by the way, another important call out on this is if you're following along at home and you're watching this video or whatever, at this point you need to make sure your Raspberry Pi is turned on and double check that you've turned on the SSH service, because we're going to be connecting to it over SSH. And the I2C service is the one that I always forget to turn on, and I always get an exception that is I've got it listed somewhere in the notes. I always get that exception, and I go, oh, that's because I forgot to turn on the I2C service. Use the Raspberry config command and make sure you turn on the I2C service. That is probably the number one thing you're going to forget while you're doing this module. All right, so .NET has two types of publishing modes: framework dependent and self-contained. Framework dependent is when you have the .NET runtime installed in the operating system, and all you have to deploy are the assemblies that come out of your project, right? And whatever other dependencies they might have. A self-contained deployment contains all that plus all the runtime, so you don't have to have the runtime installed in the operating system. I like to use self-contained deployments for my IoT devices just so I don't have to worry about, oh, what version of the .NET runtime is on there. It doesn't matter. What version of the .NET runtime is on there is the one that I need, because it goes out with my app. The downside to this is that it's much bigger. The deployment footprint goes from being maybe 10 or 15 megabytes up to around 80 megabytes. So that's a concern. So what are we going to do to get it out there? So the first thing we're going to do, I'm going to clear my terminal there. I'm going to actually open a Windows terminal. Here we go. I'm going to zoom that guy in, clear it again so it refreshes my nifty little prompt. And I'm going to SSH out to my Raspberry Pi device. Now, if you have changed the host name of your Raspberry Pi, then you're not going to SSH to Pi at Raspberry Pi. You're going to SSH to Pi at my host name or whatever you named it, right? Or maybe the IP address will also work if you know the IP address, okay? But Raspberry Pi. So there we go. And what's his password? Now, if you are doing a lot of this, deploying things to a Pi and testing over and over again, I strongly recommend you look into passwordless SSH. Passwordless SSH is a method by which you can generate a certificate on the host device that you can put on your client device that serves as automatic authentication. So you don't have to type that password every time you SSH in. Now, I'm on my Raspberry Pi device. This is the one on my desk. You can see there's nothing in my home directory. So I'm going to make a directory. I call it my cheesecave.net directory. Nothing in there. All right. So that's the first part. Now back on my device here. I'll do this in my Visual Studio Code terminal window. I'm going to publish my app. .NET publish -R is what says do a self-contained deployment targeted for a specific runtime. And which runtime am I targeting? I am targeting the Linux ARM runtime. So it's going to go build, and it's going to go do all that. And whoops, wrong button. And this is the location where we have all of our files. And mine says net 6.0. Yours might say net 5.0. I'm using a preview build of the .NET 6 SDK. This is all the exact same code. It works in either. So let's real quickly see what's in that location. So there we go. Now we've got, so there's a cheesecave.net shim. That is basically the command that we'll use to launch our application in Linux. We've got, the binary, the assembly that goes behind that. We've got, There's iot.device.bindings.dll. We've got a whole bunch of Linux runtime requirements there that I don't even know what they all do. Keep going. Somewhere in there we have system.device.gpio. Yeah, I don't know where that is. Would help if I remembered my alphabet. System.device.gpio. Unitsnet. That's the assembly I was talking about that does the conversion. So there's all of our different files that go along with this deployment. We're going to copy them over there. I'm going to go back over to my terminal. I'm going to clear it again so it resets my prompt because it's driving me nuts. We're going to SCP. So that's secure copy. That's built into OpenSSH, which is what gives us the SSH command in Windows and Linux. I'm going to copy all the files from that location. Make sure you include the star, right? The asterisk for all. I'm going to copy them to Pi at Raspberry Pi. So that's username at hostname, right? Colon, and then you specify the location on that device, which is going to be my home folder / cheesecave.net. And again, it prompts me for my password. And again, you can avoid this if you set up SSH for passwordless access. And I mistyped my password. There we go. It's copying all those files. It's going very quick for me because I've got a really fast Wi-Fi network here in my office. It might go slower for you, depending on your network. So there we go. We're done. We're copied. So there's one other step that we have to do. So let's verify all those files. Yep, they're all here. There's one other step that we have to do. That cheesecave.net file, the executable, the shim that I said that's going to, trigger our assembly and run the code. It's not executable. We're in Linux, and binary files aren't trusted. They aren't allowed to execute unless they are explicitly given the execute bit. So we are going to set that execute bit on our file. And now we can run it. Fingers crossed. You know what I did? This is important. I didn't save my code. Compiled that original program.cs. Whoops. I can fix that. I mistyped my password again too, because I have one of those really clicky mechanical keyboards. And if you hesitate at all, it registers as a double keystroke. All right. So coming back over here, let's run that code again. Hey, I think it worked. Right? So that looks like 73 degrees and 48% humidity in my office right now. Can we call up my desk so we can see the device? Yeah, so let's do, we probably can't do a view that shows both my screen share. Wait, yeah, we can. Can we do the one that's like it's like the third from the right, the one that shows my screen share? Can we put my desk there instead? Yeah, that's what I wanted to do. All right, so I'm going to zoom this way in, zoom it way in so everybody can see. All right, so enter command. So we have my status command that just writes it out again. Let's see if the fan command works. I'm going to turn the fan on. Fan. We have a fan. I mean, it's an LED, but it's a fan. All right, let's turn it off. Let's turn it on again. Let's turn it off again. You guys have no idea. If you've never done this, this is super addicting, right? Being able to manipulate real world stuff like little LEDs and relays and stuff in code. It's the most powerful feeling in the world, and I love it. So that, my friends, I believe, let me check the content. Let me check our content for the day. I think that's the first part of our workshop. We tested the app. We just did this part. We can skip that. Yep. What to do if something doesn't work. This is important. So let's review this real quick before we call it a day here on this part of the workshop. If something doesn't work, first, double check all the connections with the diagrams. All right. Make sure you've got the I2C service enabled. Okay. Make sure you're using the right address for your BME 280. If you're using the Adafruit one or some generic ones, it'll be the default I2C address. If it's not, a lot of the generic ones, however, use the secondary I2C address. If you need to debug the code remotely, you can. You can use Visual Studio or Visual Studio Code to connect to the Raspberry Pi remotely. That's beyond the scope of this discussion today, but we do have it documented with an easy walkthrough. And then lastly, if you're just not sure that your BME 280 is working or your I2C bus is working, which I have had, I did buy a pack of those generic breakouts and one of them did not work. And you want to test it, there is an I2C detect tool that you can install on your Raspberry Pi that will help you troubleshoot that. So that is all there is to using the .NET IoT libraries to construct Internet of Things devices with .NET.
Well, that was amazing. You didn't see me, but I also got very excited when the light turned on. It did feel like a little bit of magic there. So that was awesome. I hope all of you following along were also able to get the light to turn on or are able to do it in the future when you watch the recording. We have a ton of great questions here. We're really good on time. What do you say? Should we bring a few questions on in?
Let's bring in some questions.
Excellent. Okay. And we also have Laurent in the chat as well answering questions. So you mentioned that .NET runs everywhere and that this works for that, but does this work for F# or for Visual Basic VB?
The short answer is yes. You can consume the .NET IoT libraries with VB and F#. In fact, I was recently contacted by a community member who looked at all of the samples. Can we throw my screen up there again real quick? Yeah. So in the resource links, we have a link to the .NET IoT Libraries documentation. And I was recently contacted by a community member who went through these 4 tutorials over here, and he loved them. And he said, I've been going through these with my daughter, but we do VB instead. Would you like for us to contribute VB samples? And I said, sure. So that's something that we've actually got in motion right now as a community member is converting the samples that I made for these tutorials to VB. If somebody out there is an F# person, I'm not, but I have friends who are. If you're an F# person and you would like to do the same, please by all means, go right ahead.
Excellent. Yes. And I wanted to bring Laurent on as during the Q&A,
Hi, Laurent.
just add another expert.
Hey.
Yay, party's all here. Yes, as you heard, we are always accepting folks who are working on different technologies, and we do, as an open source project, always looking forward to those. We have a couple questions from YouTube. Can you talk a little bit about the industrial protocols like Modbus, TCP, and RTU, and Ethernet, IP, all that stuff?
So some of those terms that I just heard, I don't actually know the definitions of. Laurent, how about you?
Yes, I know some of them, but not really by heart. The key point is that, yes, there is limited support for some of them in .NET IoT. Now, for anything which is Ethernet, anything which is networking, that's part of the OS. That support is with .NET, whatever platform you are using. We're using the OS for that, so that's fully transparent. I see another question about Mqtt. So of course you can use Mqtt. You can connect to Azure. You can do all of that. All the networking part is supported. Now for things which are more specific, there is part of the support for those ones. And PR welcome, as you say. Jane, it's open source, so I mean, contributions are welcome. We do have a couple of people who have already been contributing in some of those very industrial protocols.
Excellent. Yes, is it possible to integrate more sensors using a serial protocol?
Yes, it is. You can use the normal serial support. System.io.port is supported for all platforms. Some of the bindings are using that, some of the NFC readers, for example, and some others. So yes, of course, you can use it.
Ah, excellent. And I know you answered this in the chat, Laurent, but is the IoT library available for C++?
Well, any language that supports .NET can consume it. Okay, so Cam already answered about VB. So if you are doing .NET development with C++, then yes. If it's native C++ without .NET, that's going to be a bit more complicated. So no, in this case. Okay.
Okay. Let's see. Can you talk about other frameworks out there besides IoT libraries? There's a lot of chat about Windows IoT, but Cam mentioned a few other ones.
So I'll start this one. Excuse me. Coffee went down my windpipe, and that's not helpful. So I'm just getting into the Meadow, the Wilderness Labs Meadow. I had a great conversation with one of their developer advocates the other day. They actually have their own library. This device doesn't use the IoT, the .NET IoT libraries. They have their own that they're actually going to open up, they said, to additional boards. So that's one example I can think of as far as other libraries. What about you, Laurent?
Oh, well, I can think about .NET Nano framework running on devices like this one, ESP32, STM32, so it's very complementary. And the interesting part in there is that all what you've shown, Cam, you can do it with an ESP32, for example. With the .NET Nano framework, it will be almost exactly the same code, almost exactly the same thing. The reason is because the API are aligned. So you can use, and we've been porting as well a lot of those bindings to .NET Nano framework. So you have the BMP, it's using as well UnitsNet. So it's very, very easy and very, very simple. And the experience you have is the same. You can debug with Visual Studio 2019. And that's another one. But that's for MCUs, right? And as you explained, Cam, at the beginning, that's for very little processors when you have a little bit of space. But there are advantages as well that runs on a battery, for example, or on a solar panel. You cannot really do that seriously with a Raspberry Pi, for example.
Now, I do need to, I think that question, was asked in such a way that I need to clarify something a little bit. I need to differentiate between Windows IoT Core, which is an operating system, and the Windows IoT libraries, which those were created to run on Windows IoT Core and do a lot of the stuff that the .NET IoT libraries do today. The .NET IoT libraries are based on the Windows IoT libraries, except they run in .NET, .NET Core, and will run basically anywhere. And including Windows IoT Core, right? So basically what we're saying is the Windows IoT libraries, I wouldn't so much bother with those. I would go here first. Even if you're developing for Windows, use these libraries instead.
Even if you're developing for Mac, you can run .NET IoT on a Mac and with a simple extension. For example, you can have a GPIO and I2C, SPI, you can have all this fun as well. Do not really care about the OS behind. Just have to be a .NET lover, and that's it.
Great. Well, you both actually mentioned a few really amazing technologies for IoT, Meadow, Wilderness Labs, and also Nanotech. And we actually spoke with both of those teams, and we have a couple demos for you to kind of elaborate a little bit more. for Nanotech and Wilderness Lab. So if now's a good time, I say we queue up that video for the demo. All right, let's see.
Hello, I'm Laurent Lerbach. I'm Principal Software Engineering Manager at Microsoft. And today I'm with José to speak about .NET Nano Framework. José, can you introduce yourself and explain us what .NET Micro Framework is?
Sure, Laurent. Hi, I'm José Simões. I'm the CEO of Faculty Solutions, one of the co-founders of .NET Nano Framework and recent Microsoft MVP on developer technologies. About Nano Framework, .NET Nano Framework, it's a framework that allows you to write C# code for small constraint embedded systems like ST microcontrollers, ESP, and all those. To get you started with it, the best place to go is to our GitHub organization, where you can find several repos that can help you with that. For example, there is the samples repo, where you can find pretty much code samples for every API that we have available, from the infamous Hello World with blinking and LED to complex projects connecting to Azure IoT. There is also the IoT device bindings, which we share with .NET IoT Core, that help you get started with pretty much every device that found out there, like sensors, stepper motors, buzzers, wherever you are up to, you'll find almost certainly the Mqtt there for it. Also, there is the firmware for the various devices,
On the firmware side, José, I see ESP32, STM32, TI, NXP. Are those the only boards supported, or I mean, because I see like different numbers, or you can support many others, like
we have support for other boards. These are the reference targets, the main ones, and we also have the community boards, which are provided by community members. Those kind of expand the reference ones. They also target the same platforms of the reference ones.
And what I can propose, you can do a demo maybe to see.
Sure.
So the blinking one is usually the best one, right? So here I have some code. It's very simple. It's a device GPIO. I create a pin. I open the pin. The number 2 is the embedded LED, and what it will do is just like change the state of the pins. And I put a breakpoint. You see, it's already deployed. It's already on a breakpoint, and I toggle the value, which means like it was off, as you've seen. Now it's on. I have the capacity to see the variables. I can add them to the watch, for example, and I can see them here. I can continue, that will pause again. I can change the value here, as you would do in a normal .NET application. And if I continue, I should have, of course, here now one more, which is 11, because I change my value. I can remove the breakpoint. I can continue like that and do, I mean, pretty much what I'm used to do when I'm developing in C#. Do you have any question for me, José, on this demo?
Yes. Why do you have all those 3 Mqtt reference there?
Oh, the nuggets. It's because in Nano Framework, we do have a lot of nuggets like you are used to for developers. They are just smaller than the normal ones. We are trying to break things down to keep the size very, very small. And here you can see like you really have hundreds of them. And you already mentioned that we have things from IoT device and a lot of devices that are already pre-set up. So you don't have to write the low-level stuff with SPI, I2C, etc. That's fully transparent for you. You just say I have this device, give the pins, and all the magic happens.
Cool. So you just grab exactly what you need. You don't have to bring everything all the time to make your firmware image huge.
Absolutely. And we have a beautiful getting started guide, which will guide you on how you can make your first application in minutes. It's about installing the Visual Studio extension. It's about tools to be able to flash the device, and it's about creating your first blinking application, of course, because we are in embedded world.
All right. Also worth mentioning that if you need help, the best way is to go to our Discord server. On there you can find a friendly and helpful community where you can ask everything about your development, discuss ideas, suggest the new stuff that you want to work with, and interact with community members.
Thank you, José, and looking forward to see all of you in .NET Nano Framework.
Thank you. Have fun with .NET Nano Framework.
Well, thank you, Laurent, for pre-recording that demo for us. That was amazing. I think, so yeah, we do have one more demo for you all talking about Meadow from Wilderness Labs. Adrian was kind enough to give us a demo on that as well. And so let's go ahead and run that.
Hi, everyone. My name is Adrian Stevens, and I'm a program manager for Microsoft's Developer Relations. And I'm also an advisor for a company called Wilderness Labs. And Wilderness Labs makes a platform called Meadow. And Meadow's really pretty amazing. Meadow enables you to build embedded apps running on microcontrollers using full .NET. And this is the same modern .NET you'd use for other platforms. Today it's using .NET Standard 2.1 and .NET 6 is coming soon. So this is not a slimmed down IoT specific development package, it's full .NET. And being a modern .NET platform, it has strong security posture, so it's built for enterprise. It includes something called Meadow Cloud, which allows customers to monitor, update, and manage hardware over the air out in the field. So why does Meadow exist? Well, traditionally embedded development on real microcontrollers is, well, it's hard. And it's often done with languages like C, and it's written by people with deep expertise and a lot of experience on specific hardware platforms. And so Meadow is here to try and drastically reduce that time to market for hardware and really make embedded development much, much easier. And we're in the midst of a bit of a quiet revolution. So the last decade, we all heard about mobile. But something has happened. The world is rapidly deploying smart technologies and embedded computing, or IoT, and it really is the new epoch. Like in my lifetime, we've gone from this vision back in the 80s, the Bill Gates quote of, a computer on every desk. Well, we've now gone to a place where we can literally put a computer in everything, everywhere. And this really is a consequence of that mobile revolution that brought us this amazing hardware and commodity cheap sensors and microcontrollers and parts. And what's happening now is this IoT market is now more than 3 times the size of the mobile market. And in just a few years, there's going to be 10 times more non-mobile connected things on the planet as people. 75 billion connected things by 2025. This is bringing a real shift in the culture of development. So nearly everyone now is tasked with building IoT. Companies that previously would never even consider building hardware have now hired teams dedicated to IoT, to microcontroller development. And a lot of these teams, well, honestly, they're failing. They're failing early, which is good, but they're still failing, and that's bad. We're in a market where there's a real lack of skilled IoT developers. We have a lot of non-embedded developers that need to build hardware. And so Wilderness Labs has set out to make hardware development as fast and as easy as doing web or mobile apps. So for Meadow, there's no real tool chain setup. You open Visual Studio, you hit File New, or it's as easy as opening up the terminal and typing .NET New. So you're not fighting with makefiles, you're not setting up compilers, you're doing .NET development like you would for any other .NET platform. And part of the magic here is the IoT stack. So it does all that cool, complex real-time OS stuff on the bottom, but Meadow puts these layers on top of it, so you don't have to learn real-time OS programming. You use your .NET skills using the Meadow stack to build pretty fantastic hardware applications. So build hardware like software. So if we look on the left, imagine we want to control a servo. Sounds like a complex thing. Well, with Meadow, we would instantiate a servo object, new servo. You tell it where it's plugged in physically onto the Meadow board, and possibly pass in some specific configurations, in this case, the type of servo it is, and that's it. And now we can interact with the hardware in software. It's just regular .NET coding. And this really opens up a world of opportunities. Wilderness Labs has invested heavily in creating an open source driver library to control all of these peripherals, all of this hardware. So of course you can do things like make games, you can build rovers and robots, you can build intelligent devices that can measure distance or sound or take pictures. And of course it's a .NET platform. You can integrate with Azure, you can integrate with the Xamarin mobile application, commonly over Wi-Fi or Bluetooth. And this is a really fantastic platform to build enterprise hardware and enterprise IoT, but also a really fantastic platform for learning .NET development. Thank you very much. I love the .NET community. I love seeing all the innovations happening here. If you want to learn more about Meadow and Wilderness Labs, head on over to www.wildernesslabs.co.
Excellent. Well, thank you, all of our good friends at the Wilderness Labs and showing us Meadow. And also thank you, everyone from Nanotech, Laurent, and your team. We have a few more questions that I want to get to before we getting on to our next portion of the second workshop. And I'll just go ahead and read those right along down.
Sure.
Great. So what about deploying .NET 5 or 6 to Raspberry Pi and run the development entirely on the Raspberry Pi?
You can do that. There's a caveat, however. The caveat is that for debugging and IntelliSense in like Visual Studio Code or, well, Visual Studio Code is all you're going to be able to run on Raspberry Pi that has, that has C# functionality built in. There is a dependency on a project called OmniSharp. OmniSharp is installed as an extension in Visual Studio Code. It's the C# extension. I forget what it's called exactly. OmniSharp does not run on ARM devices. So you can develop, you can write your code, you can compile your code. It's kind of slow. Like the SDK is really not optimized for that environment. You can do all that, but you're not going to be able to debug it, and you're not going to be able to get IntelliSense.
I see.
Yeah.
I see.
For that, I would recommend to use a normal Windows Linux or Mac device and use an extender that will provide you I2C SPI and GPIO like the FT4222, the FT232H, or even just a simple Arduino that you can use as a extender. All this is supported in .NET IoT.
Funny you should mention that, Laurent. I just got in the mail my FT232. I'll show it up there.
Cool.
Come on, focus. Anyway, this is one of the boards that Laurent is talking about.
Yeah.
Here, I'll throw it over on my desk. Maybe
And you just plug it and you install a driver, and then you get really the all the beauty on your main machine, PC, Mac, Linux. It doesn't matter. For development purpose, that's really the best. And you can then enjoy best environment, either Visual Studio if you love it on the PC, either VS Code if you love it on Mac. It doesn't matter. Then it will be much more efficient.
Yeah, so here on the one end, we have just a little USB-C connector. And yeah, you can plug it right into your Windows machine, and it gives you, these pins are basically the equivalent of all these different holes on the board that I haven't soldered a pin header into yet. These are essentially the same as, I won't say the same, but very similar to the Gpio header on a Raspberry Pi. And it's basically giving you a Gpio header on your Windows device.
Excellent. Good timing on the delivery there.
Right?
Yeah. Okay, so Laurent, you had mentioned this in the chat, but I'm just going to address it here for everybody. What other boards are supported? Is the ESP32 supported by .NET as well?
So that's for .NET Nano Framework. .NET Nano Frameworks works on MCUs, so those little things. So all the ESP32 family that's supported, STM32 as well, and then we have like some NXP and TI boards supported as well. We have like some flagship board if you want, those where we put a bit more support, and then we have a lot of community boards as well. And to create a board with any processor, any STM32 one, for example, it's a matter of a day. And then you have your own custom one where you can then have the fun of running .NET on an MCU.
Gotcha. Excellent. So, okay, let's move on. What kind of architecture should I use to read stats and control IoT apps from a web API? For example, a Blazor WASM app or Azure Iot Hub?
Oh, that's a very open-ended question. There's lots of different ways that you can do it. Funny you should mention it, though. The second half of our workshop today is about Azure Iot Hub, which actually provides that kind of functionality that you're looking for. It allows you to make it easy to get information from and send commands to an IoT device over the cloud, which then you could just abstract away behind like your WASM app or whatever other UI you want to build.
Yeah, so good. So good timing on the question, because we will actually cover that in the second portion of this event. And it looks like our friends got to speak at some of the Wilderness with some of the Wilderness Labs folks. We do know that they are sold out. They sold out in one day, which is amazing. Congrats for them. It says that they're allowing pre-orders, so keep on the lookout for that. So, okay, well, should we get started on the next portion then?
Yeah, okay, let's bring my desktop up, and we'll start on the not my desk, my screen. Sorry, my mistake.
It's okay. we have a lot of cameras going here.
Yeah.
All right, so Laurent, thank you so much for joining us for the Q&A. You will still be hanging around in the chat if you can.
Yeah, I'll be on the chat.
See you later, my friend.
Thank you.
I love hanging out with that guy. All right. So, yeah, what are we going to do? We're going to talk about Azure Iot Hub. Now, I'll be honest. I just kind of discovered Azure Iot Hub this month, preparing for this this discussion we're having today. We were looking for some kind of content that would take what we did with the .NET IoT workshop that we did a minute ago and extend that. And I found this great Learn module. And we've made a short URL to get there, aka.ms/learn-azure-iot-hub. And that takes us to this Learn module, remotely monitor and control devices with Azure Iot Hub. Let's just hop right into the introduction. Now, if you read this introduction, it's going to look pretty familiar when you get down to the bottom. Because when we wrote that .NET module and we wanted them to go together, we said, we're going to go with the same scenario and the kind of the same, we want to monitor temperature and humidity in this cave. So these two modules were really kind of designed. The .NET module was really kind of designed to go with this Azure module that preceded it. This module will also support Node.js if you're more comfortable in JavaScript than C#, but we're going to be doing all the C# today. So we'll hop right in. So the very first step that we're going to do, if you're doing this module and you come to this module, you're going to see a big button right here that says activate your sandbox. And remember I mentioned earlier about Microsoft Learn? We have this ability to do sandboxes that give you free Microsoft Azure for a limited amount of time to learn with. I went ahead and activated mine so we wouldn't have to wait on it. You're going to have an activate button, and it'll take like 2 or 3 minutes to activate. And then you'll be able to launch the Azure portal, right? So I'm going to just middle click on that guy and create to create a new tab. Wants me to sign into the Azure portal. Okay, and once you're here, you're going to go to create a resource. You're going to search for IoT Hub. And you're going to click create. It's going to want to know what resource group you want to put your resource in. And there's only one resource group available to me in my sandbox, and it's been created for me. And that's this learn dash followed by a GUID. So we'll pick that guy. We're going to name our hub. We're going to name it Cheese Cave Cam Soper. I'm actually going to name it 3 because this is my 3rd one today because I've been preparing for this part. And pick a region close to you, geographically close. If we hop over to the networking tab, there's nothing we need to change there. We hop over to the management tab, there's nothing we need to change there either, but I am going to go ahead and draw your attention. Actually, you know what? Instead of zoom it, let's zoom in on the browser. There we go. I'm going to draw your attention to the pricing and scale tier. The standard tier is selected by default. Standard tier, they even give you pricing down here that is it showing me my pricing? No, it's not showing me my pricing. If you go look at the pricing calculator, it's $25 a month for up to 400,000 messages a day. I did the math. Actually, let's do the math again. Where's my numeric keypad? So let's say we send one update message from our device every second. So that's 60 seconds in an hour. 60 seconds in a minute, rather. 60 minutes in an hour times 24 hours in a day. That would be 86,400 update messages per day if you sent a message from your device every second. So that S1, if you're just doing one device, that S1 is plenty. There is a free tier as well, right? So we could select that, and that's limited to 8,000 messages per day. That'll work for a lot of devices too. Obviously, you just wouldn't want to, send update messages quite as frequently. We're going to go ahead and leave it on standard because we're not playing with real money here. We're playing with a sandbox, so there's no reason not to. There's some other settings down here. Earlier, it had when we came in here and it was set to S1 standard tier. It was also set to 4 device to cloud partitions. That's just how they divide up the queues for incoming messages from your devices. 4 is plenty for most applications. In fact, for what we're doing today, we could turn it all the way down if we wanted. I'm just not going to bother. I'm just going to leave it alone. And we can go next, review and create, and gives us all of this, validates our choices, shows, here we go, here's the pricing, $25 per month. And then we could click create. Now, I'm gonna go ahead and click create, and it's gonna take me to this deployment in progress screen. There we go. And it's gonna set here for an indeterminate number of minutes. Because that number is indeterminate and because I was planning ahead, I've already provisioned one of these things. I provisioned it while we were watching the videos a minute ago. So this is CamSoper 2. CamSoper 1 actually glitched and is still deploying. So we're going to use number 2 here. There was a moment of panic in there when I wasn't sure it was going to get done, and I just anyway. So we've created our IoT Hub. There's a couple, just all defaults. There's a couple of things we need to do to configure it. The first thing we're going to do is we're going to go down under Explorers in the menu here, and we're going to select IoT devices. You see we have no devices. I'm going to add a device. And I'm going to name this, you can name it whatever you want. The workshop uses Cheese Cave ID. I would have said like Cheese Cave device, but I'm just going to go with what the module lists. And there's nothing else we need to change. We're just going to create it. Okay, it says there are no IoT devices to display. I've had this happen to me a few times. Just refresh and it'll list. All right, so there it is. And we're going to go into the device, and it lists, let's look at what we have here. We have the ability to send a message to that device. We have the ability to invoke what's called a direct method. We'll get to that in a little bit. We have the ability to look at something called a device twin. We'll get to that in a bit too. But for now, what we're going to do is we're going to take this device. We're going to come down here to where it says primary connection string. I'm going to copy that. And I'm going to pop up an instance of Notepad, and I'm going to paste it in there. Since this is this device is transient, this thing is going to go away after this workshop. So I don't care if you guys see the key right now. So there it is. That's the connection string. So the connection string contains the host name, which you see I have the host name is actually cheesecavecamsoper2.azuredevices.net. It contains the device ID, and it contains the access key to get into it. All right, I'm going to get that off screen before somebody starts messing with me live. Now, I hope I didn't give anybody ideas. Now, I'm going to come over here to the shared access policies. That's one connection string that I need. That's the device connection string. I'm going to label that in my notepad, by the way. Device connection string. You can't see that, but we'll come back to it. And then over here under shared access policies, they've created some shared access policies for us for different identities to interact with this IoT hub. Now, we're going to grab the shared access policy that we want to use for our backend service. Now, in general, this policy right here, service, might be the one you would use for that. If we go into service, we can see service has permissions for Service Connect, and that's it. Well, we're going to be doing stuff later on with device twins and other properties that require registry read and registry write. I could add those to this identity, but I'm not going to. In fact, the module says to use the Iot Hub owner policy. I don't know that that's the best idea, because if we come in, you see he actually has everything, but for purposes of this discussion, we'll go ahead and use it. So I'm going to copy that connection string, bring up my notepad again, service connection string. And you can see that connection string looks very similar, same host name, except instead of defining a device, we're defining the shared access key name, and then we actually provide the shared access key. And then I need one other thing. I'm going to come down here to where it says built-in endpoints. And that built-in endpoints, that's where they provide other endpoints, other ways to interact with the IoT Hub that use other protocols. For example, the Azure Event Hub that this thing is built on the back end. We're going to grab that Event Hub compatible endpoint, and we're going to make sure that it's for this shared access policy. Our choices are IoT Hub owner or service. We're going to make sure it's for IoT Hub owner. We're going to grab that endpoint, that Event Hub compatible endpoint. Whoops. Event Hub endpoint. There we go. And you'll notice that's a completely different connection string format. I mean, it has some similarities, but it's different. All right. So let's grab this tab here. I'm going to dock it here, close that tab, go back to our exercise. What's next? Make sure I got everything. Make sure I got everything. We covered all this. We did all that. All right, check our knowledge. Which IoT Hub left-hand menu entry do you select to locate the service connection string? Do you remember, Jamie?
I'm going to say shared access policies.
Okay. And which IoT Hub device and service connect? I'm sorry. All IoT Hub device and service connection strings begin with what text? Do you remember?
So I'm going to say host name because I saw it in your string.
You are right in both cases.
Yay. Congratulations, everybody who did it online.
Yay. All right. So now we're going to write code to send and receive telemetry. Right. So the first thing we're going to do, and this all talks about how we're building this basically a virtual device. This is all going to be in software. This isn't going to take advantage of the hardware device we built in the previous workshop, although I might have a surprise pertaining to that later on. What we're going to do right now is we're going to build a virtual device just in code. When you come to this exercise, make sure you've selected C#. I'm going to do it with Visual Studio Code. I did run through it with the Visual Studio directions just to make sure they were up to date and you know, applicable to what we're doing. So if you want to use Visual Studio, that should probably be okay, but I'm going to do everything in code. So from code, actually, let me open a new code window because I took my other one to a different monitor. We're going to, just like like the way I like to make new projects in code is through terminal. And go to my D directory, cd source, .NET new console, -o, and I'm going to call this one Cheese Cave Device. All right, and we're going to go into the Cheese Cave device directory, and there were a couple of packages we needed to add. Actually, 3 packages. So I'll just copy those. I'm going to clear my console here so it's more legible. I'm just going to paste in. And I'll hit enter for the last one. So we've added the packages we need, and now I'm going to open it up in code. So again, just a regular old console app. Here's our project file that shows our references that we, here, let's pop that up. Shows our references that we added. If we go to program.cs, you know, there's the standard hello world. You can guess what we're going to do here. And then they give us some code. And this code is actually a lot longer and a little bit more convoluted than would be my preference, but we're going to run with it. Really quickly, let's just step through the flow of the code. So when we launch the app, we're setting some constants here, and we're creating some static variables for like this device client thing. And oh, wait, your device connection string. And we're going to paste that into the code. Now, I hope this goes without saying, but I'm going to say it anyway. Don't ever do this, right? The connection strings in code are always a bad idea unless you're doing exactly what we're doing today, which is just like trying to learn. Then it's okay. But don't ever do it in production code, please. Please, 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 please. Don't ever do this. All right. So you use something like Azure Key Vault or whatever. All right. So let's get down to the main method, the program entry. Don't have my outline because for whatever reason I don't have my C# extension, but that's fine. We'll just roll with it. All right. Here's main. So main instantiates that device client static variable, creates it from the connection string, and then goes to the send device to cloud messages async method, which if we go to connect device to cloud messages async, it's doing some things here to simulate telemetry. It starts with an initial temperature, an initial humidity, and then it does some stuff with random numbers, basically, to just generate a new reading and occasionally generate a fake fan failure and just generate telemetry to send up to Iot Hub. That's all it's doing. It's just all this code is just doing math to make some random numbers to make it look like a humidity and temperature setting. And then the magic that we want to get to is down here, where we are creating a message. And that message contains all the different properties that we've calculated and mocked up, sensor ID and the fan alert if there's a fake alert that we generated, and if there's a temperature alert because our current temperature is outside of our desired range and things like that. We're going to build all that into a message, And then we're going to send that message on the device client. Okay, that's all this code does. It generates telemetry, sends it up to Iot Hub. Let's real quickly pop open my terminal here and got that build. Hey, it builds great. I can't remember in the steps if we are supposed to run it at this point or not. So let's check. Save, test, run the app. Okay, so we'll go ahead and run it. .NET run. All right, so it's running, and you can see it is generating fake values. 70 degrees and 99% humidity, and there it goes. It's just going to do that every so often. And that's all this program does. It's just a virtual device that is, you know, reading temperature and humidity and sending it to IoT Cloud. Exciting. We're going to leave it running, right? Now we're going to make a second app, though. So let's make a new, isn't there a new window? No, there it is. It's at the top. Make a new Visual Studio Code window. Same kind of deal. And I'm going to make another console app, .NET new console -o. This one's going to be Cheese Cave Operator. And we're going to go into the Cheese Cave Operator directory. And from in there, we are going to add, am I still in? Yep, I'm in the right place. We're going to add some packages. Again, there's some more dependencies that it has to take advantage of the Iot Hub libraries. There we go. And then we'll open this project in our existing Visual Studio Code window. All right. So, oh wait, there my C# extension kicked in this time. So we'll select the CS proj and hopefully let it do its thing. So just like before, we've got a project file, we've got a program file. We're going to blow away the contents of the program file, and we're going to copy this text in, this code. And just like before, I'm going to go ahead and say, and say, yeah, this code is a little not optimized. There's some stuff in there that I really wish the author had done differently. And I would have updated it, but because the module supports Node as well as C#, I decided it was best not to rewrite the whole module. So we're kind of paying for the fact that we're trying to keep things a little generic. Just like before, though, there's a placeholder. So what it wants here is our Event Hub endpoint. So I'm going to grab that from my text file. Go. And what does this code do? Well, if we jump down, I should have my outline now. I do, yay. All right, so if we jump down to main, it instantiates that Event Hub client. Remember I said Event Hub is kind of the underpinnings of Iot Hub? We're just going direct to the Event Hub to get telemetry this time. And we're getting some runtime information and some information about the partitions, and we're connecting to the partitions within the Iot Hub to start receiving messages, right? And we just run it as a background task, one for each partition. What does that receive messages look like? Well, every so often, where I forget where the I think it's the 100 milliseconds there. I think that's milliseconds. Is that milliseconds? Is that what specifies the time? No, I forget what's setting the time on this, and because we are pressed for time, I'm not going to go too deep into it, but every so often it polls for new messages on the Event Hub partitions, and if it gets one, it writes it out to the console. So we're sending telemetry from our virtual device, and this code is our operator code, and it's getting the telemetry from that device. And IoT Hub is sitting up there in the middle, brokering that information exchange. So just like before, let's see if it works. Build. And remember, if you will, that Cheese Cave device is still running. Put him over on that side, and I'll put Cheese Cave operator on the other. Clear my console so we can read it again. .NET run. So you see it connected to the partitions on the IoT Hub, and now it's displaying the telemetry that's being sent, which includes the temperature and humidity values, as well as the fact that the device says those are out of range. So they've added, you remember in the code back for the device, there was, it adds temperature alert and humidity alert if it's out of range. And that's what that looks like. So that's working. We're sending telemetry from this app, going up to IoT Hub, and getting it in this one. So what's next? Well, I'm glad you asked. So let's go to the next step. The next thing that we're going to talk about is how to invoke a direct method. So in interest of time, I'm going to kind of gloss over this, but remember our device, we need to be able to turn on a fan remotely. We need our operator code either manually by like a human or automatically to say, oh, humidity and temperature are out of range. Let's turn on the fan. So what that involves is a method on the device to turn on the fan and some way to invoke it from the operator code. So that's what we're going to do. So come to this step, make sure you have C# selected. And we're going to add this method, this set fan state method, to the Cheese Cave device app first. So let's go over here. Let's stop running. There we go. Terminal for now. We're going to come down here to the end of the class, and we're just going to paste that method in. And that method, here, let's Shift-Alt-F. There's no formatter for C#. Why are my extensions all messed up? That's no fun. Anyway, that method just sets the fan state, right? It takes a method request that's passed in, and if the fan state is currently failed, throws an error. Otherwise, it looks at what was passed in as the data to determine whether we're turning the fan on or off, and it's just going to display that output. That's all that does. Again, this is all just virtual. This isn't a real fan. And what's the content of this method is less important than the fact that the method exists. The method exists. There it is. Now we need to wire it up. Coming back over here. So the way we wire it up is one line of code in the main method. So let's go to main. There's main. And it says to do it after creating the device client. So here's where we create the device client, sDevice client equals. So right after that, we'll put our code that sets that callback. Now when this code basically says, hey, when IoT Hub gives you a set fan state method, I want you to invoke the set fan state method, right? When he requests set fan state, you go do the actual method called set fan state. That's all that this does. Let's make sure this builds. Yay, it builds. In fact, let's go ahead and just run it, and we'll come back to it. Okay. So on the service side, how are we going to invoke that direct method? Well, the first thing we need to do, let's go back to my operator. I'm going to stop that. I'm going to close my terminal. First thing we need to do is up top, we're going to add a couple more global variables. We have one to hold the IoT Hub service client and one to hold the IoT Hub service connection string. Now, why are we using the IoT Hub client here instead of the Event Hub endpoint? It's because the IoT Hub client is what's required for doing a direct method invocation. The Event Hub can't do that. The Event Hub, you're just reading the events coming from the telemetry device. You're not able to send things going back. The IoT Hub client that we're creating here is what allows you to send things back. So you remember over on Notepad, we had our service connection string. We're going to put that here. Oops, went too far. My usual disclaimer, don't hard code connection strings. All right. Let's go back to the exercise. What else do we have? Add the following task, perhaps after the main method. Okay, so let's add that after the main method. Where's my main method? I have my outline. Here we go. So we'll put it right here. Now I can Alt-Shift-F and get my code formatting. There we go. So when this invoke method task is started, it's going to create basically a cloud to device method name that invokes, whoops, I keep pointing at things, that invokes this set fan state direct method. And it sets a couple other parameters like how long we're going to wait. And we can also set a payload value. And for payload, we're going to set the fan state to on. The other options would be off or whatever. And then we're going to invoke that device method. If it was successful, we're going to display a success message. And if it was not successful, we're going to display a failure message. And that's all that does. And then the last thing that we need to do, so we created this task that does all that. And we created the service client variable and the connection string variable. The only other thing that we need to do is we need to actually add the code that invokes it, right? So we're going to add that to the main method. Where did it say? Before creating the receivers to listen for messages. Look, there's where we create receivers to listen for messages. There we go. Shift F. So now we're going to invoke that method and wait for it synchronously because this main isn't an async main, which if I were refactoring this, I would, but I didn't refactor it. And we're just going to run with it like that, even though that's really not a best practice. David Fowler would slap you. All right. He wouldn't slap you. He's a very nice guy, but he would have things to say. Okay, so this should build, right? Let's find out. I should save it first. Okay, so let's put that on one side. Over here we're getting telemetry, and we have the thing set up to get a callback on a direct method. So let's invoke that by running the operator code. Direct method failed. Timeout. That's interesting. That was not expected. Live debugging is fun. That is interesting indeed. What did I break? Let's see if we can find out. I'm going to check my connection strings first, because that would be the first thing that I would check. So this is my IoT Hub owner identity, my IoT Hub endpoint. That is all correct. I really could not say why it's timing out right now. let's run it again. Yeah, it looks like it's timing out again, because right away it should come right back and say, oh, we've turned it on. I think it's going to time out again. Looks like it is. Well, here, let's run. Possible that I didn't save my program before I ran it over here, which could very likely be the problem. Try that again. There, it worked. Yeah, that was my problem. I didn't, because I'm not using my C# extension on the device. It didn't work right and didn't give me warnings and everything. But you saw, let's scroll back up here. You saw right here, fan set to on when it did the direct method set fan state. So that's all it does. When we first start the program up, it turns on the fan just to show the direct method invocation. Now we're pressed for time, so I'm going to go through this next part very quickly. He says as he struggles with window management. The last thing that we're going to talk about is device twins. A device twin is just a JSON document in the cloud. And what that document does is it represents the state of your device that is somewhere else. Your device just updates the twin and says, hey, the current temperature is X, the current humidity is Y. And then that way, when you need that information, you don't have to query the device directly. All you have to do is query the twin in the cloud. It's much faster and hopefully cuts down on communication directly to the device. So I'm not going to step through this code entirely. I am just going to copy and paste it, though, so we can see device twins in action. This code goes into the backend app at the end of the class. So let's pop him up at the end of the class. Stop execution. And what was, how do we invoke that? I'm sorry, I keep forgetting to see where it goes. Before the line's creating a service client in main. There we go. So there's a service client, so that's going to go here. So this is the code that says, hey, connect to the registry, connect to the digital twin, rather, and update the properties. That code should run now. And then on the device, we are going to add at the end of the class and then we need to add a callback. So the callback just says, hey, whenever you get properties that are being set on the twin in the cloud, I want you to go make those properties on the twin happen on the actual device. I'm sorry, I keep forgetting to look to see where that's supposed to be pasted. Lines after the statements, creating a handler for the direct method. So let's go to main. Right there after the direct method call. There we go. Running the device, and .NET running the back end. All right, so I can take you now back to our Azure portal, and I can show you, if we go to the device, and we go to our device twin, this is that JSON document is updated every time that the code sends an update to update the twin. You can see it has the current desired values that were set by the operator code, and it has the current reported values, which is just echoing back the desired values in the code right now. Now, in a real scenario, the reported values would probably be actual values instead of echoing those values back. And funny, we should mention that we have a way to do actual values. So we're going to bring back from our first workshop, cheesecave.net on the Raspberry Pi. Okay. And we're going to, I know I'm pressed for time, so I'm going to try and do this quickly. We're going to go to this URL, aka.ms/.net-iot-azure-sample. And this is going to take us to GitHub for now. Later on, it'll probably take us to an actual nicely formatted sample in the .NET Samples browser, but we didn't have a lot of time. And we're going to go to program.cs. We're going to grab all the code from program.cs, copy it, and go back to cheesecave.net and paste it in. I don't have time to walk through this code. I did refactor it some. Basically, it combines everything from this second module, this Azure IoT Hub module. It combines that with all these connection strings and stuff, combines that with the GPIO stuff and BME 280 stuff from the earlier module. So we actually have a real Cheesecave device now. All right, so we need our device connection string. Let me grab that. Where did I leave Notepad? There it is. I have too many monitors. All right, cheesecave.net, there it goes. Your connection string here. Save. We're gonna publish to my Raspberry Pi that is still on. Wait, what are we doing? Oh, I forgot to add. I got project references I forgot to add. So what I'm going to do is I'm just going to come over here and I'm going to get this CS proj, and I'm just going to paste it in. There we go. .NET publish. SCP. And we don't even need to run the operator program now, okay? Because we have the ability to interact with the device twin in the cloud. So I'm not going to bother with the operator program. I'm just going to deploy this to my Raspberry Pi. So here's my console from the Raspberry Pi. We're going to run it. That should not be what we saw. Did that not? This is the problem with going too fast. What did I forget? Oh, no, that is what we should see, I believe. All right, let's find out. So there's my current temperature, my current humidity off my BME 280. Let's go to Azure. There we go. I delete my Azure window. I did delete my Azure window. Tab. Home. Cheesecave. IoT devices. IoT Hub. Retrieving devices. Come on. We have places to be. All right, let's look at the twin. Unfortunately for this demo, it is not working right away. However, it was working prior to the demo today. We're pressed for time. I don't have time to debug it. The long story short is this twin should reflect the values of your cheesecave.net device. And you can also come in here and invoke that direct method, set fan state. You can set fan on, or you can set it off, and the light will light up accordingly. Unfortunately, this is the wow moment of today's workshop. It didn't work, but that's how these go sometimes.
That's okay. This is a live stream and a live demo here. That was amazing, Cam. Really appreciate you taking the extra time to kind of walk through those extra steps. This was all recorded and will be uploaded on our YouTube and all of our amazing channels, Learn TV. Thank you so much for everyone who was able to join today. We really appreciate it. Cam, thank you so much. This was amazing. Thank you for our Wilderness Labs folks who came in to help give us those other amazing demos and all the things that you can do with IoT and .NET. Laurent, thank you so much for moderating. And we have just a quick promo video, as we have a huge conference coming up in November called .NET Conf, and you will not want to miss it. Trust me. And yeah, thank you so much and have a great day, folks.
Thanks. Bye.
Save the date for .NET Conf 2021, November 9th through the 11th for the .NET 6 launch. .NET Conf is our annual free 3-day virtual developer event co-organized by the .NET community and Microsoft, sponsored by the .NET Foundation and our ecosystem partners. For 3 days, you'll learn from featured speakers from the community and .NET teams at Microsoft, talking about .NET 6, C# 10, Azure, Visual Studio, and more. This is your chance to learn, ask questions live, and get inspired for your next software project. We've got wall-to-wall content for web, mobile, cloud, desktop, games, services, libraries, and a variety of platforms and devices, all with .NET. Everyone is going to learn something, no matter if you're just beginning or you're a seasoned engineer. Don't delay. Head to www.dotnetconf.net. That's .NETconf.net to learn more and tune in.